right, so the next thing that you need to know for the Unit 3 exam is going to be some properties of the nucleus. So this is called nuclear physics. So first, you should know that inside the nucleus are protons and neutrons. You should know that protons are positive, neutrons are neutral. Okay, then you should have a rough idea for how big the nucleus is. It's small, so you don't need to know that particular number, 10 to the negative 14th meters. Okay, but you should have an idea for that if you were to take a single atom and blow it up until it's the size of a football stadium, then a P would represent the nucleus. So the nucleus is very small compared to the atom. Okay, then the density is very, very big because the volume is very, very small. So density is the mass of an object divided by its volume. So the smaller the volume gets, and the nucleus is very small, then that means that the density goes up. So you don't need to know the number, but it's 10 to the 17th kilograms per cubic meter. And so this gives you an idea for just how dense the nucleus is. All right, then you have isotopes. So you should know what an isotope is for the exam. It's the same element, meaning it has the same number of electrons in orbit and it has the same number of protons, but it has different numbers of neutrons in its nucleus. And so there's a special way of writing the nucleus of an atom. And so, for example, this is going to be called carbon 12. So that's one way of writing it. But a more explicit way of writing carbon 12 is to say that it's carbon, and then this number down here is going to be its atomic number, the number of protons, and then this number up here, where the 12 is at, is the number of protons plus the number of neutrons in that particular isotope. So to find the number of neutrons, you take this number minus that number. So that 12 minus 6 is 6, so that this particular isotope would have 6 protons and it would have 6 neutrons. So here's what could be on the exam. I'm going to give you the isotope, I will give you the periodic table, and then you tell me how many protons does it have and how many neutrons does it have. All right, this slide is not going to be on the exam. It is going to be very important if you're going to study chemistry. So on your periodic table, you also have numbers that have decimal points. And that is where those decimal points are coming from. That's the averages of the different isotopes for that particular element. Okay, then you should know the two nuclear forces inside the nucleus. So you should know that the strong nuclear force is what's holding the protons and neutrons together inside the nucleus. And then the weak nuclear force is the one that can change a proton into a neutron, or it can change a neutron into a proton. So that's all that you would need to know. Now, there's also some other particles that are emitted. So that's that beta particle, the B thing, and then the neutrino, which is that V looking thing. So those are some other particles that come flying out whenever a proton changes into a neutron or a neutron changes into a proton. But all I want you to know is that the weak nuclear force can change a proton into a neutron or vice versa. Okay, let's talk about nuclear fusion and nuclear fission. So nuclear fission is when you start with a large nucleus like uranium. So uranium has an atomic number of 92. So it's a big nucleus. And so when it breaks apart into two smaller nucleuses or nuclei, then that is going to emit energy. And so this is going to be nuclear fission. On the other hand, nuclear fusion is the exact opposite. You're going to start with two small nucleuses, like hydrogen, and smash them together, and then that turns into helium. And then that is going to release energy. So notice that small nuclei undergo nuclear fusion and large nuclei undergo nuclear fission. So what element is not too small and it's not too big? That turns out to be iron. So iron is going to be larger than hydrogen, and it's going to be smaller than uranium. And the thing about iron is that when you smash iron, you fuse it, it will not give off energy. No nuclear explosions. If you take iron and you pull it apart, you fission it, it will not give off energy. And that's going to be critical because we're going to find out that when stars begin to manufacture iron, they're going to explode. Okay, another thing you should know is that all the nuclear power plants on Earth undergo nuclear fission. And the sun does the nuclear fusion thing. Okay, you should also know some nuclear chemistry. And so this means you need to be able to add and subtract numbers. Bring a calculator. I've had students that they have difficulty manually subtracting numbers. So bring a calculator with you when you come to take the test. Just remember that the arrow, which says yield, so how you would read that would be hydrogen, when you smash it into helium, yields, turns into lithium. So that's how you would read it. But what you're going to see on the exam is something like this. So we're going to take lithium and we're going to smash it into beryllium, and we want to know what does it turn into. So you have to supply the numbers and you have to supply the symbol of what it turns into. So in order to do this, you're going to add the top numbers. You're going to add the bottom numbers. Okay, then you'll have your periodic table and you will look up on the periodic table the bottom number, the atomic number, because that is a unique number for each element. And then once you know what element it is, then you put that down. So here's an example of another nuclear reaction where you're starting with something and it turns into copper plus what else? And you have to supply the numbers and you have to supply the symbol. So this time it's going to be subtraction. Think of that arrow as an equal sign and then just either add or subtract. Okay, where does the energy come from in a nuclear reaction? So the energy that is given off in the nuclear explosion is going to be the energy that was being used to hold it together. So we call that the binding energy. And as you can see, nuclear binding energy is a lot more powerful than chemical binding energy. Okay, and now let's calculate the amount of energy released in a nuclear reaction. So this could be either nuclear fission or nuclear fusion. So both instances use the same formula, E equals mc squared. So after a nuclear explosion has occurred, after a nuclear reaction, the pieces parts that are left over, when you add them all up, is less than the original stuff that you began with. And you'll notice it's true whether we're talking about nuclear fission, that's the picture on the left, or nuclear fusion, that's the picture on the right. So that after the reaction, the mass is less. That missing mass is what goes into the formula. So here's the kind of question you should be able to answer. I will give you the missing mass. Now, I might not give it to you in kilograms. You should know how to convert from grams to kilograms. Okay, and because kilograms is the official metric unit for mass. Okay, then you can put it into the formula, and notice it's E equals mc squared. Okay, c is the speed of light, which I would give you on the exam. You have to square it, and then take that number and multiply it by the mass, and then that's going to be the energy that's going to be released. Don't forget to put the J on the end of it. So that's the official metric unit for energy. Okay, so let's take a break, and when we come back, let's talk about general properties of the sun.